Hi, I'm Brian Sidlauskas at Oregon State University, and I'm here to speak about the unexpected findings that resulted when we tried to test the validity of an enigmatic genus of anostomid fish in a total evidence phylogenetic framework. And I'd like to begin by acknowledging the efforts of all my co-authors, especially Fernando Assega, who shares the lead authorship of this project. I'm speaking today about my favorite family of fishes, Anostomidae, which contains about 150 species and is the second largest family in Caracoideae, a megadiverse suborder of about 2,000 species that mostly inhabit the neotropics. Anostomids demonstrate marked variation in their mouth position, dentition, and coloration. And as a really neat recent developmental study by Lefeo et al. Showed, they also have substantial ontogenetic plasticity of their oral jaws. As shown here, a new paper in Systematic Biology with Bruno Mello as the lead author also reveals that Anostomidae is one of 3 caracoid families to have experienced a marked acceleration in diversification about 30 million years ago. That means that Anostomidae produces species more rapidly than almost any other segment of one of the world's most impressively diverse clades of fishes. That remarkable acceleration occurred during one of the most geologically dynamic periods in the history of Amazonia. Over the course of about 20 million years, we see various stages of the uplift of the Andes, marine incursion and regression, the formation of expansive sub-Indian wetlands and the Lago Peva system, river capture events, and the eventual eastward redirection of the Amazon. Hydrological shifts during this period could have very plausibly helped build the incredible richness of the modern neotropical ichthyofauna. However, it's noteworthy that not all branches of the caracoid tree of life seem to have diversified similarly during this period. Even though all the modern caracoid families existed by 30 million years ago, only 3 of them accelerated their diversification, while the rest continued to pump out species at the background rate. This intriguing result begs the question of what made early members of Ceresalmidae, Anostomidae, and Characidae special. I'll return to this question at the end of the talk, and if you're interested, our paper in Systematic Biology contains some more speculation about the clade-specific factors that catalyzed diversification in all 3 families. For right now, I'd like to zoom in to discuss just one anostomid genus, Anastomoides. This enigmatic genus has long been diagnosed by a putatively transitional tooth and mouth morphology, and it contains just 2 species, both described more than a century ago. The validity of Anastomoides as a genus has been quite uncertain, because no phylogenetic study has ever included both species, and because the studies that have included one or the other have returned very different placements. The left image illustrates the placement that I got for Anastomoides atrianalis in 2008, using an entirely morphological dataset, while the right shows Betancourt et al.'s more recent inference for Anastomoides natareri using a phylogenomic approach. The topologies are very different, but does this result from actual conflict between molecules and morphology, or does it just reflect different origins for different species? So, to find out, we launched a study to test the validity of Anastomoides by synthesizing molecular and morphological data in a total evidence framework. That quickly expanded to include a comprehensive osteological examination of Anastomoides natareri once we realized how bizarre its internal anatomy was. And then finally, we explored ancestral state reconstructions and what they can reveal about the morphology of the ancestral anastomids that began radiating so furiously in the early Oligocene. And I really want to stress that this is the first study to ever include morphological data for one of the 2 Anastomoides species, and also to take a moment to show off these beautiful osteological dissections and photographs that my colleagues Fernando Assega and Jose Birondelli produced. Ultimately, we were able to link 158 morphological characters to multi-locus Sanger sequenced molecular data for about 55 species, primarily synthesizing existing data, but also generating new sequences and osteological observations for the 2 species of Anastomoides. We inferred a total evidence phylogeny in BEAST2 with the Clade Age plugin, which allows time calibration using 4 fossils. Ancestral state reconstruction and the ACE package used the MK model for discrete characters and thus took advantage of branch length information. And it was immediately obvious that both data sets recovered exceptionally high levels of divergence between the 2 Anastomoides species. They differ for 20% of the morphological characters known to vary in Anastomidae, and they're 16% divergent at cytochrome oxidase 1. In fact, Anastomoides naturari isn't very similar to any anastomid in either matrix, and it's only slightly more similar to members of the in-group than it is to members of other caracoid families. So what's going on here? Well, as you might have guessed, the phylogenetic results return wide separation of these 2 species, and that central insight holds when we analyze the morphological and molecular data sets in isolation. Unexpectedly and excitingly, Anastomoides naturari appears to be the only living member of an anastomid lineage that diverged early in the history of the family at least 30 million years ago. It has been evolving independently ever since. That really long branch subtends a species with a fascinating mosaic of derived and ancestral character states. These ancestral state reconstructions in the figure at right highlight 4 very different patterns present in the dataset, some of which reverse the polarity of characters that I investigated in my doctoral thesis more than a decade ago, or reveal new instances of convergence. In a 12-minute talk, I can't get into all the intricacies of anastomid osteology, so I'd like to focus on just one of the ways in which the new study alters our understanding of anastomid evolution. Specifically, I want to call attention to the autopalatine. Most, but not all anastomids have a prominent, laterally directed process on this bone, and this obvious feature was one of the clearest signals that originally helped me to formulate a hypothesis of relationships within the family. When did this process arise, and was it present in the ancestral anastomid? Here, I'm replicating an image from De Tovo and Castro that shows the placement of that process in a lateral view of a Leporhinus skull. The process lies just dorsal of the region where the various components of the adductor mandibulae complex coalesce to insert on the maxilla and dentary. And it just so happens that the 2 nominal species of Anastomoides differ in character states here. One lacks the process and one has it. So my take home here is that adding just one taxon or changing a coding decision can have a big effect on an ancestral state reconstruction. This slide shows 4 different ways of looking at this palatine character. The right panels include Anastomoides naturari, the left ones excluded. Including this taxon greatly increases the likelihood that the most recent common ancestor of the family lacked the process in question. The contrast between the top and bottom panels shows the also large effect of coding the process as definitively absent in the outgroups, which we did in our new paper, as opposed to using an uncertain coding, as I and Richvari did in 2008. These 2 tweaks serve to completely reverse the interpretation of which character state is primitive and which derived. They also change our reconstruction of the morphology possessed by the most recent common ancestor of all anastomids, indicated by the angled arrows. So why should we care? To answer that, I'll take you back to this slide, which shows how 30 million years ago, anastomids began to diversify at a rate exceeding that of most other caracoids. Why? Did special features of their anatomy or ecology help to catalyze their exceptional diversification, not only in species richness, but also in jaw morphology and coloration? To answer that question, we need to be able to reconstruct the ecomorphologies that anastomoids possessed during the period in which their diversification took off. Based on what I've shown you here, it appears that the unique combination of character states in Anastomoides naturare and its early branching position can help clarify the sequence of innovations that occurred during the family's initial diversification. Not a bad feat for a fish that has been rarely studied since its description in 1876, and one that really makes us wonder what else remains to be discovered when we look more closely at organisms that we thought we knew. To wrap up, and since we clearly could not retain both species in a polyphyletic genus, I introduced to you the world's most newly recognized anastomoid genus. Anastomoides naturare is now known as Insperanos naturare, from the Latin insperans, meaning unexpected. I suspect that we have only just begun to discover the unexpected insights that will result from exploring its anatomy and natural history. We thank our funders, most particularly the US-Brazil Fulbright Program and the Brazilian agency CAPES. We also thank the numerous people who provided loans, collection support, and assistance with logistics and analysis. Finally, I thank my wife Ray and daughter Fiona for their perseverance and understanding when the COVID-19 pandemic erupted during our Fulbright Fellowship, leaving us locked down in a rented apartment for months with only this borrowed microscope, Insperanos, and each other for company. Thank you.